This is Unit 7 in AP Calculus ABA, Applications of Derivatives. Lesson 3, Connecting Derivatives of f with the graph of f. So we're going to basically help discuss or give ideas for how we can determine what the graph looks like based on the derivative and the second derivative. Okay, so I'm going to put up an example here. Let's consider f of x. Let's change the color here. F of x equals x cubed plus 11x squared plus 20x minus 32. Okay. There are a number of things I can tell already. I know this is a cubic function. I know that cubic functions have at most two curves, two changes in direction. So something like this. I know that this has a positive coefficient, so it will be down on the left and up on the right. Okay. What I don't know is how deeply, or whether it does this, or down and up, or how far it goes. I also don't know where the peaks occur. And so those are very valid questions to ask and to answer. All right, so let's go ahead and give this a try here. First thing I might do is take the derivative of f, 3x squared, plus 11 times 2 is 22x plus 20. And where the derivative is 0, we have a flat point, right? So it's 0 here and here. So I'm interested in finding those places. So set the derivative equal to 0 to find, we call them critical values, places where the derivative is 0. Other critical values to be included are cusps and corners as well. So any place where the derivative doesn't exist. In this case, this is a polynomial function, so the derivative exists over all real numbers. Okay, so let's see if we can solve this here. I'm going to go ahead and just save myself some time and use the quadratic equation. So I'm going to pull up Desmos. So my cat has decided to join me here. Now, Desmos.com. Oh, Desmos. I feel like Mickey Mouse Clubhouse. Oh, Toodles. Oh, Desmos. Okay, so A is 3, B is 22, C is 20, come on, C is 20, and we're going to do negative b plus square root b squared minus 4ac all over 2a. And we get negative 1.06, okay, and minus, we get negative 6.27, okay? So it doesn't come out very nice here. But let's go ahead and go with it here. So negative 6.27 and the other one was plus negative 1.06. We could take it and get exact answers as well, but they would involve a square root. Okay, and so this is where its critical points occur. So the question becomes: is each critical point a maximum or a minimum? Now, based on what I know about this function being a cubic and being a positive leading coefficient, I'm quite certain that the left one is a max and the right one is a min. But we can verify that otherwise as well. So this is negative 6.27, and this is negative 1.06. Okay, but we can verify that. And one way to verify it is to test the first derivative to the left and the right. If the derivative is positive to the left and negative to the right, we have a maximum. If the derivative is negative to the left and positive to the right, we have a minimum. Okay, that's one way. I actually prefer this. Taking the second derivative to determine the curvature. Okay, and let's find the second derivative. 3x squared becomes 6x, 22x becomes 22. Okay, and we're gonna examine this second derivative at these points. So the second derivative at negative 6.27 is 6 times negative 6.27 plus 22. 6 times 6 is 36. So this is going to be negative something, okay, less than 0. Okay, when the second derivative is negative, we say it is concave down. Concave down, because the second derivative determines concavity. At the point negative 6.27, it is concave down. That makes this a maximum. Okay. F double prime of negative 1.06 is 6 times negative 1.06 plus 22. That's about negative 6 plus 22 is going to be some positive quantity greater than 0, so it is concave up. Concave up. And therefore, this is a minimum value. A minimum value. Okay? And let's go ahead and verify it with our graph in Desmos here. Verify our results. All right. So let's see here. And let's call this A equals, okay, not A equals, capital A equals, there we go. And capital B equals, and let's just copy this. Okay. And we'll graph here f of x equals x cubed plus 11x squared plus 20x minus 32. Okay, and let's graph x equals A and x equals B. Okay. And it's giving me an hourglass. I don't understand. Okay, I can't do that, huh? All right. X equals negative 1.06. Oh, it doesn't understand it because I put it as a single expression. I need to separate it. Oh, and A and B are the same here. Let's do this. Negative. There we go. Now we got it. All right. Okay. And it's hard to see here, so I'm going to change the scale here. Let's do the x-axis from negative 8 to 0. There we go. Now we got it. All right. And you can see that is the peak right there, and that is the trough right there. Okay, now there's another point of interest as well, right here in the middle. It's where it changes from being concave up to concave down. And that's called the inflection point. So we're going to set the second derivative equal to 0. Where the second derivative equals 0 is the inflection point, the dividing line between concave up and concave down. Subtract 22, 6x equals negative 22. X is negative 22 sixths. As a fraction, a mixed fraction, or mixed number, it's going to be negative 3 4/6, or 2/3. Negative 3 2/3. And so what happens here is that negative 3 2/3, x equals negative 22 sixths. Right there is the inflection point. That's the dividing line. That's where there is no concavity. There is no, it's neither concave down nor concave up at that point. To the left, it's concave down over the entire domain. To the right, it's concave up over the entire domain. And so there you have it.